Alrighty, we are on 3.1G, which is about relative velocities. We are going to cover this and 3.1H, which from your readings you notice that they are more or less the exact same thing, just said with a lot of words and in a couple different ways. So we're going to start by looking at 3.1G. So in this section, the main point of this section is that motion is relative to the observer. And there were a couple different examples that we looked at in 3.1G. We looked at several different examples of airplanes and some different examples of riverboats or boats on water. So boats on rivers specifically, actually, not just water. Okay, so the main thing we got from these examples, which I'm going to go over in more detail in a second, is that we must describe motion like different types of motion relative to an observation point or to an observer. So we're going to have to say relative to the ground or relative to the person standing on the bank watching this boat, right? Because we're going to see that motion is different on a boat than it is. So, for example, the velocity of a boat on a river is going to feel different. Well, not feel different. It's going to we're going to see it differently when we're on the boat. When you look at the speedometer, for example, it's going to have a different velocity on the boat than someone would have on the bank of the river, the side of the river, watching the boat go by. If the boat is going with the current, it's going to be going faster than the speedometer says that's on the boat, right? If it's going against the current, it might look like it's going slower. If it's going with a cross current, it will look different that way too. So we have to describe motion relative to an observation point or person. So let's look at these examples. We're going to look first at airplane examples. And we're going to look at 3 different scenarios with airplanes. We're going to look at tailwinds, headwinds, and side winds or crosswinds. And you might be asking yourself, like, okay, what is the point of this? And the point of this is we're putting into action all of the things that we've learned. So these last 2 sections are just real-world examples of the physics that we've learned so far in 3.1. So specifically the boat and plane and hot air balloon or balloon examples that we're going over. These are all real-life examples of the vector addition and the vector component stuff that we've been doing so far in this section. So when we have a tailwind, we have I'm just going to put the picture up here. Okay, so here we have our plane, and the tailwind is a wind pushing on the back of the plane. Okay, so we have our plane, and let's say that our plane is going at 100 kilometers per hour. Kind of slow for a plane, but whatever. So our plane's engine is pushing the plane at, let me move this guy. Come here. Let me put it right here. It's pushing our plane forward at a velocity of 100 kilometers per no, I guess that's, 100 kilometers per hour in the exactly south direction. So a tailwind is occurring on the plane. It's pushing on the plane also. The tailwind is the wind that pushes against the back of the plane, so it's going to be back here, pushing the plane back here. It's in the same direction that the plane is going, is another way you can think of this. We can say it like that as well. All right, so we have a tailwind of 25 kilometers per hour. So this is an example of why we have to specify the position that we're observing this plane from. Because from the ground, the plane looks like it's going faster than it looks like it's going from inside the plane. Because inside the plane, The speedometer reads 120 or 100 kilometers per hour, right? The engine is pushing the plane forward at 100 kilometers per hour. But from the ground, we see the plane moving with this velocity from the plane's engine plus the velocity from the tailwind that is pushing the plane forward. So the resultant velocity here is going to be, we just add these two together because they're in the exact same direction. So the resultant velocity from the ground, which we have to specify again, relative to the ground, we'll say even down here, from ground, the resultant velocity is 125 kilometers per hour in the southern direction. That's pretty simple. We have been doing this for a long time. We understand that. That's not really new information. And headwinds aren't really new information either. So headwinds, instead of wind that pushes against the back of the plane, the headwind is the wind that pushes against the front of the plane, or the wind that is pushing the plane in the opposite direction that it's already going. All right, so here we have our plane again, and it's going in the same direction, same southern direction at the same velocity. But now we have a headwind. The headwind is pushing on the plane in exactly the north direction at 25 kilometers per hour. So now we have two vectors that are going in opposite directions. So remember, when we have vectors going in opposite directions, we subtract them. So our resultant vector is going to be 100 minus 25, which is going to be 75 kilometers per hour in the southern direction, and this is relative to the ground. We'll say from ground, or from ground. All right. So this is also not really a new concept, and it's not really, this is pretty old. I think we did this in the first I can't remember when we did it, but it's been a long time. So this isn't new information. Crosswinds are kind of more the combination of the things that we've been doing so far, or in this section at least. Sidewinds, crosswinds, same thing. So a side wind or a crosswind is going to be wind that pushes against the side of the plane in a perpendicular direction. So now we have this plane going forward at the same velocity that we've been dealing with the whole time. But now we have a side wind or a crosswind that is going to be 25 kilometers per hour in the western direction. So now our resultant is obviously going to be a little bit different, right? Our resultant is going to look like we have a 100 kilometer per hour vector, and we have a 25 kilometer per hour vector. So our resultant is going to look like this. So the plane is going to be going, actually, we don't know the direction that it's going to be going in, and we don't know theta. We don't know this theta, right? And we don't know the speed or the velocity at which it's going either. So now we're going to have to figure out the magnitude and the direction of the resultant vector by doing Pythagorean's theorem and the trigonometric method, right? So if I wanted to do that, of course, there we go. So if I wanted to do that, I could solve using first Pythagorean's theorem and then the trigonometric method, right? Pythagorean method and then the trigonometric method. And I would find that relative to the ground, the plane is traveling. This is how we would report our answer. So you're going to get graded on whether or not you can report your answers correctly, right? Like you need to say, like I'm going to ask you to write sentences write a sentence explaining, this is in the homework today. All right, a sentence explaining or giving me the direction and the magnitude of the object, whatever it is. In this case, it's the plane. So in order to do that, you would say the plane is traveling 103.1 kilometers per hour in a, well, it would be 14. Theta is 14, so it would be 270 minus 14. So the direction that it's traveling would be 256 degrees counterclockwise of east. So, sorry, let me start over. The plane is traveling at 103.1 kilometers per hour in a 256-degree counterclockwise of east direction relative to the ground. Or you could say, relative to the ground, the plane is traveling at 103.1 kilometers per hour in a 256-degree counterclockwise of east direction. So either of those that would be acceptable. Okay, so this is the airplane example, and this exact same thing can be applied to the boat examples. So now we're going to look at boat. It was technically riverboat. Riverboat examples. In the riverboat examples, I'm going to write these in green, we had current, not wind. So in the riverboat example, what's equivalent to a tailwind would be a forward current. A forward current. And this is the current that pushes against the back of the boat. Of course, making that boat go faster, appear to have a greater velocity from the side, from the bank, where we're watching this boat. Then we have, instead of a headwind, we have a backward current. And this is just the current that pushes against the front of the boat. And just like with the plane and the headwinds, this is going to decrease the velocity, the relative velocity of the boat. Then finally we have a cross current or a side current, whatever you want to call it. Cross current. And this is the current that pushes against the side of the boat and causes or in a perpendicular direction of the plane or the boat's forward motion. So it's the exact same thing as a crosswind, but it's in a boat situation, so it's with water and against the boat. All right. So these are all the examples of the airplane and the riverboat. There's not really much more. We're going to look at one example of the type of problems that you're going to see on your homework. But really quickly first, I'm going to cover the one really main section or main component of 3.1H. All right, so remember that 3.1H is about the independence of perpendicular components of motion. So perpendicular components of motion, each of the components of a vector are independent of one another. So remember that the vector components describes the effect of a single vector in a given direction. So there's two components of every angled vector, remember. All right, so remember there was our definition of a component. It's a part of a 2D vector. And we don't even have to say, a 2D vector, meaning that it's going in a direction other than north or south or east, west, left, right, up, down, right? So we could also call this, I've been calling this an angled vector, right? A vector that's going at an angle that's not one of our four main directions that we've been talking about that are on a compass. So this is what a component is. Remember, every angled vector has two components. So the main point of this whole section is just to tell you that perpendicular components of vectors are independent of one another. So the examples that we were doing before, when we have a crosswind or a cross current, for example, let's look at some of those examples. And look at how both of the vectors, the components, are independent of one another. So if I have a boat, this is my cute little sailboat, and it's going across a river, this direction, at 3 meters per second, and there's a cross current acting on the boat in this direction, also, let's say, of 2 meters per second. So if I draw my resultant here, I would have something like this, right? This would be the direction that the boat is going in, right? And I, of course, can figure out let's do 2 meters per second here. I can figure out the exact direction and the velocity of that resultant by doing a bunch of math, the Pythagorean theorem and the trigonometric method. And I would get, rather than doing all of that, I'm just going to give you the answer here. Okay, so this is the solution for that. So when I have a cross current pushing on the boat at 2 meters per second, and the boat's engine is traveling, pushing the boat forward at a velocity of 3 meters per second, I get this vector diagram, and when I solve using Pythagorean's theorem and the trigonometric method, I find that the boat is traveling 3.6 meters per second in a 304 counterclockwise of east direction, and this would be relative to the person standing on the bank watching, okay? So, the whole point of this section is to show you that the perpendicular components of vectors are independent of one another, meaning this vector doesn't have any effect at all on this vector. The cross current has no effect whatsoever on the forward motion of the boat, or the forward velocity, I should say, of the boat. So we could, an example of, or showing you that how this is true, is we're going to do the exact same thing, but we're going to increase the cross current. So say the current picks up and the boat is now being pushed with a cross current of 4 meters per second instead of 2 meters per second, like this. Okay, so now we have the same velocity from the engine of the boat pushing the boat forward at 3 meters per second, but now we have a cross current pushing the boat 4 meters per second. Okay, so our resultant is going to look differently. It's going to have a different magnitude, and it's going to have a different direction. And it would be specifically 5 meters per second at a 323 degree counterclockwise of each direction. Not at. So we see here that our resultant has changed, right? The overall magnitude that the magnitude of our velocity is increasing, and it's going at a larger angle, right? The boat is moving at a larger angle counterclockwise of east. However, our forward motion, our forward velocity stays the same. So we could increase this cross current, this velocity, by 1,000,000 times, and no matter what, this is never going to change here. This will always remain the same. And the opposite is true also. If I increased the speed of the engine, if I pushed the engine to go faster, increased the velocity of the boat, but that would have no effect on the cross current, right? So all I would be doing is extending this arm and keeping this arm the same, right? So I would extend, if I extended this to 6 meters per second, it would be like that, and the 4 meters per second would stay the same. So now I would have a different resultant with a different magnitude and a different angle. But it does nothing to the one vector component does nothing to the other vector component. It cannot increase it, it cannot decrease it. They are independent, completely independent of one another. So again, there we have the two vector components are independent of one another. And we see that in this example above because a change in one of the components does not enhance or decrease the other component at all. They are completely independent of one another. Okay, so that's pretty much it for these two sections. We're going to do this example because this is going to be kind of similar to your homework assignment. So it says that a motorboat. We're going to do this example. I'll write example here. Example number 1. We have a motorboat traveling 4 meters per second east, and it encounters a current traveling 3 meters per second north. All right, so the first question I want to know is what type of current is this? Well, we can determine what type of current it is by either looking and seeing that we have an east and a north, and knowing that those are perpendicular. Or better yet, we could draw this little diagram. So we have our boat, and it's traveling 4.0 meters per second in the eastward direction. 4.0 meters per second east. And we have it's encountering a current traveling 3.0 meters per second in the northward direction. So if I draw these two vectors as a vector diagram, I have 3.0 meters per second and 4.0 meters per second, and my resultant is going to be like this. All right, so there I can see that these are perpendicular vectors, so this is a cross current. If it was a forward current, then it would be going this way, 3.0 meters per second, in the same direction that the boat is traveling. If it was a backward current, it would be traveling 3.0 meters per second in the opposite direction, in the westward direction. But because it's traveling perpendicularly, it is a cross current. So that's A. B wants to know what is the resultant velocity of the motorboat. So very simply, we are going to use Pythagorean's theorem to solve for that. So I have assigned each side A, B, and C. A squared plus B squared equals C squared. So A squared is 3.0 squared plus 4.0 squared. And when we add those together, we get C squared. When we plug this into the calculator, we find that the resultant velocity is 5 meters per second. And like earlier, we found that this angle was 323 degrees counterclockwise of east. Okay, so that was B, and now C says here that if the river is 80 meters wide, how much time does it take for the boat to travel shore to shore? This is where it gets kind of tricky. Okay, so we have to draw a diagram like this. So we have the boat starting here at the start and finishing here at the finish. So this speed here is the resultant. We're going to call this C, and this is the 5.0 meters per second in the 323 counterclockwise of east direction, right? Okay, but what we're given is that the width of the river, so this is the river, the width of this river, sorry, that is not what I meant to draw. The width of this river is 80 meters. That is not the same as this distance from here to here, because what we've done is we've found velocity, the average speed when we're traveling from start to finish. We haven't determined anything about the distance that we travel, right? So we are traveling from start to finish across, but this is 80 meters that we're talking about, right? So if we were to assume that we were going to travel straight across, we would use the boat's speed in this situation, which was 3.0 meters per second, right? So if we travel at 3.0 meters per second for 80 meters, how much time would it take for us to get across, right? So we can't use our resultant here. So what I'm saying is we cannot use 5.0 meters per second in order to solve this, because this isn't 80 meters. This is 80 meters, right? The width here is 80 meters. We also can't use this horizontal component of our velocity either, which was 4.0 meters per second, because this is the river's speed, right? And we don't know this distance either. We don't know the distance from where we should have ended if there was no current and where we actually ended because of the current. All right, so if the river is 80 meters wide, how much time does it take for the boat to travel shore to shore? So in order to solve for this, we have to do a couple of steps here. First, we need to remember that distance equals velocity times time, right? So we have to rearrange this because we're just looking for the time that it takes to cross the river. Divided by V, so we get D divided by V equals T. Okay, so we're going to use this idea that we were just talking about back here, right? Where was it? Sorry. A change in one component does not enhance or decrease a change in the other component. So we're traveling 80 meters straight across, and we are going to have a velocity of 3.0 meters per second. So 3.0, oh, the distance, sorry, I'm doing that wrong. Distance should go on top. Distance is 80 meters divided by velocity, which is 3.0 meters per second. That's going to equal the time that it takes for us to cross the river. So I get that it takes 27 seconds for us to cross. All right. So it takes 27 seconds for us to cross the river here. The next part that we want to know in part D is what is the distance downshore that you arrive. So we should have arrived here, but we actually arrive here. So what is the distance downshore that we arrive? Okay, so since I'm trying to find this horizontal component of distance, I'm going to use the horizontal component of time. So I want to know the distance. Remember that distance equals velocity times time. So which velocity do I use? Well, I'm looking, like I just said, for that horizontal distance. So I'm going to use this horizontal velocity or speed as well. So I'm going to use 4.0 meters per second. And what time do I take? Well, it takes us 20 seconds to go across the river, no matter what, right? It takes us 20 seconds to get across the river, so I'm going to use 20 seconds here. When I plug this in, I find that the distance downshore is 80 meters. So this distance here is also 80 meters across. It should have stopped here, but it ends up 80 meters down the shore. Okay? So that is a pretty complicated example, but you will have one more of these that you're going to do. It's from the reading from yesterday. So that will be part of your homework for today. So for the rest of the day, you can work on the 3.1 GH questions. We are done with 3.1. You will have a quiz next Thursday over section 3.1. I will give you the study guide tomorrow, and we'll have tomorrow to do some I'll give you some information tomorrow for some review, and then possibly one more review next week on maybe next Monday, or I guess tomorrow. Yeah, maybe Monday. Okay, that is it. Please let me know if you have any questions or if you need help on the homework. Tomorrow we're going to be doing the rest of our homework corrections, but I'll also give you the study guide tomorrow. So anyway, okay, that is it. Thank you. Have a good day. Goodbye.